right, the last couple of days we've been looking at a process called antiderivative, taking some type of an equation that describes a slope or a rate of change and trying to work backwards to figure out what function did this come from. You know, what was the original f of x or the original revenue function or whatever that described the situation. Today we're going to try to make a connection between geometry and this idea of antiderivative. Okay? And so this will start out maybe as a little bit difficult in concept, but I think as we start to go through it, it's actually going to become fairly simple. Okay? If we can just keep a few things in mind that I'll stress as we go through here. Okay? So the idea of this section here today is we're trying to relate this geometry concept of area with the definite integral. This is our topic here for today, trying to relate these two, what appear to be completely different ideas, see how they're really tied together and how this is really a big breakthrough for us when we talk about calculus. Okay? Let me pick a really simple example here to begin with. A lot of times, real-world situations, we will let the time component be along the x-axis. You know, whatever time units we're in, usually that's what we call an independent variable. We're going to let time vary. But there's a lot of times when instead of knowing what the height of the function is or the distance of the function or something about the original, maybe we know something about the rate of the function. And so I might put a r of t up here, standing for rate at time t. So I know the object's speed at a particular time. Okay? And I want to pick, like I said, I want to pick a really simple example here. Let's say that we hop in a vehicle and we start driving down the interstate here, and we drive at 70 miles per hour. Okay? And so if I drive at 70 miles per hour for 3 hours, okay? Just a really, really simple example. We all know that we have traveled 210 miles over the course of those 3 hours, just simply 70 times 3. Okay? Graphically, what that would look like is what I'm doing is I'm graphing this speed or this rate. I'm going to graph 70 on my graph here. Okay? So wherever 70 is at, I'm going to graph a line because I'm driving at 70. I'm driving a constant distance or a constant speed the whole time. Okay? I drive this until I get over here to 3 hours. We'll just assume we started at time 0. Okay? And my question is where does the 210 show up in this situation? You know, we know it's 70 times 3, but geometrically, where does that show up? Well, the height of our rectangle is 70, and the width of our rectangle is 3. And what do we get when we multiply the height times the width? Well, that's the area of the rectangle. Okay, and so that's the connection between these two here, is that the area under a curve, okay, is equal to this total distance. I'll put an equal sign here, equals total distance. Okay? So the area underneath of this, and it's not really a curve because I'm starting with a really simple example, a straight line here, but even if we had a curve type shape here, if we can find the area underneath of that object, okay, that's going to give us the total distance traveled by this vehicle, or the total distance that a particle moves in sciences, or whatever. Okay? So that's what this is related to, and that's how area is tied to what's something called an integral. Okay? Now, I haven't necessarily used these words yet, but I want to go ahead and make a few more connections here. We've used symbols for integrals before, but I just don't think I've used the language itself. An integral, for what we need to know, an integral is basically an antiderivative. Okay? And so we're going to make that connection that area underneath of a curve is an integral, and then integral is an antiderivative. So we can make the connection that area will be found by taking antiderivatives. Okay? That's the first connection we have to make here. Okay? The second thing I need to point out is how this will be written for us. Okay? If I was trying to solve this problem in calculus, this is what it would look like. I would make our little antiderivative symbol. Okay? Along the lower and the upper spots of that elongated S there, I put the boundaries of, in this case, t. I'm saying I want to go from time 0 to time 3. Okay? So these are always like x values down here. They're always the independent variable. Okay? So I'm going to go from 0 to 3, and my speed from 0 to 3 is just a constant number. It's just 70. Okay? So I would put a 70 right in here, and then at the end, because t is my variable, I would put a dt, just to remind the user that t is going to be the independent variable. Now, if we were to solve this problem, okay, using antiderivatives, now just ignore this for just a second here. What's the antiderivative of 70? 70 times x, or in this case, we'll just go 70 times t, since that's what I used for my variable here was t, right? Okay, so 70 times t plus some constant here, okay? And then what we will learn here as we progress is, well, now once we have this, what do we do with this 0 and this 3 to be able to go ahead and find out that this answer really is 210 miles? Okay? But I'll stop at this point. But that's the connection that I want to make, at least at this stage, is how these are all related together in the fact that we can find areas, or total distances in this case, okay, by doing antiderivatives. Okay? Now, let's look at another example, just a different situation here. What if I give you this problem here and I say find the area from 1 to 3 on 5 minus x dx? Okay? Just in terms of a problem, just geometrically, what does this look like? And I don't really want to do antiderivatives yet. I just want to solve this with geometry for right now. Okay? 5 minus x, this is a linear function that starts at 5, and it has a slope of negative 1. Okay, so this is 5 comma 0, this is 0 comma 5. Okay, and I want to find the area between x equals 1 and x equals 3. And I know that it's x equals 1 and 3 because it's a dx problem. Okay, so I want to come in here and I want to find the area from x equals 1 to x equals 3. Okay, that's my goal, is to find this area. All right, any ideas on how we can use geometry to do this? Because I want this area in here. Okay, well, that is a geometric shape that has a formula, but most people don't remember it, so probably what do we want to try to do here? If your job was to find this area here, how would you break this down?
Make a rectangle and a triangle.
Sure, make a rectangle and a triangle out of it, exactly. Okay, since, like I said, this is a trapezoid that has a formula in geometry, but it's so hard to remember. So we just split it down into easier sections, rectangles and triangles. And so now let's go ahead and find the area of this rectangle, and then let's add it to the triangle, and we'll have our answer. Okay? Well, we know the rectangle has a width of 2 down here. My question is, what's the height of this rectangle? Close. It should be 2, right? Okay, and the reason that it is 2 is because I know I'm at an x-coordinate of 3, okay, and I know my function is really 5 minus x. So if I subtract that 3, if I sub that 3 in there, 5 minus 3 is 2. The other geometric idea that this slope is negative 1, right? So if I go down, if I come over to 1, I'm at 4. If I go over to x equals 2, I'm at a height of 3. If I go over to 3, I'm at a height of 2. So we kind of walk our way down one step at a time. But either way, this is the ordered pair 3, 2. So the total area of this rectangle is just, it's a 2 by 2. Okay? So that total area is 4. Okay? Now, what if we come up here to the triangle? Okay? Well, I still have a base of 2. Okay? This time, though, what's my height? Well, what's this ordered pair right here? 4, right. If I sub in 1 to my function, I get 4, so I'm at 1 comma 4. So my base is 2, the height is also 2, because I'm going from 2 to 4. Okay? So over here I've got base times height, and then because it's a triangle, I have to multiply by a half. So base times height times a half. And if we go through and calculate all this together, that looks like another 2, 4 plus 2. It looks like this total area from 1 to 3 needs to equal 6. Okay? And this is one thing that we should be able to do is if I give you a shape like this, where it can be broken down into nice, easy geometry formulas, rectangles, triangles, those types of things, that we should be able to solve this just using a geometric approach, not really worrying yet about antiderivatives and how this will be worked out with calculus. Okay? All right, good. So there's that example. What about this one right here? Now, I might have to give you a little more help with this in terms of just getting started, but once I think I get you started, this will be fairly simple again. Okay. First question I've got, does anyone know what this square root of 16 minus x squared, what that is the graph of? And this isn't the most common thing that you ever graph. Like right away, I hope everyone knew this was a line. This one's not quite as obvious. But if you plot it out, what you're going to see, this is going to be the upper half of a circle. Okay? Right? It's kind of the equation of a circle, but it's been solved for one of the variables. Okay? So what we've got here, the upper half of a circle centered at the origin, and its radius is 4 because we have a r squared of 16 in here. Okay? 1, 2, 3, 4. And so this is the picture that we end up with. And if you didn't know this, you would just graph it on your calculator and you'd see it generate the upper half of a circle for you. Okay? All right. Now, the question that we want is we want to find the area from -4 to 0. So the area that I am interested in is it starts right here and it just keeps going, but then it stops when it gets to 0. And that's the area that we're interested in. Okay? Well, how can we use geometry to solve this? Without doing any antiderivatives or anything fancy, how can we just use geometry to figure this answer? The clue that I gave you was that this was a upper half of a circle, so what do we know about circles and their areas? Close. Pi r squared, right. Okay. So the formula for a circle is pi r squared. Now that's for an entire circle. Okay. What percentage or what part of the circle do we have here? We have a fourth, right. We have a fourth of a circle. So all I need to do is take this and divide it by 4. That's my formula for this quarter part of a circle. And then the last step is going to be to sub in the radius. And in this case, the radius of my circle is what? It's a radius of 4, right. So I would replace the r with a 4. I can go through and make this calculation, and that will be the area that this is equal to. Okay, now, what we will start showing next time, we won't do this today, but what we will start showing next time is that if we were able to take the antiderivative of this and be able to plug in some values into that antiderivative, that we would get this exact same answer. Now, thing is, some problems are actually much easier to solve with geometry. For example, this problem here, once we realize this is a circle, this problem is very simple to solve with geometry. I mean, we had this thing done in 20, 30 seconds. Okay? If we were trying to take an antiderivative of this thing, we would be going for a while because this is not a very easy antiderivative to take. So there will be times when we will fall back on this geometry method because it is actually easier in some situations. There will be other situations where the geometry formula will not be very easy to use, where we might not have a straight line or a circle. We might just have some weird looking curve where we don't have a geometry formula. And that's what we'll be talking about next time is how can we use the calculus, the antiderivative, to solve those groups of problems. Okay, so that'll be our difference here. If we can use geometry, yeah, feel free, go ahead and use it because sometimes it's actually easier. Okay. All right, now the question that comes up is what if we don't have a nice geometry formula? How are we going to solve these questions like y equals x squared? The antiderivative of x squared from 0 to 1. Okay? Now, if we look at this via a graph, we know that this is just a parabola starting at the origin, and it goes up to, let's just call this point 1, 1 here. I'm making this a really zoomed in graph. We need to be able to see this pretty well. Okay? And if we draw a line down here, just a dotted line, the area we're interested in is this little region underneath this curve right here. Okay? Now, how could we figure out that area? Because we don't have a nice, geometry formula. This is definitely not a straight line. It's just a curve. So we don't have a good way to solve this, or at least we don't think we do at this point. Okay? Well, back in the history, the first thing that they would try to do is try to make this as close to a nice geometry shape as they could. And the first thing that they probably tried was to just come in and turn this shape into a triangle. And they would go through and find the area of this triangle is just 1 times 1 times a half. So they figured out the area of this triangle is a half, and so then they just gave their answer. They said, well, the area underneath this curve is less than a half. We don't know exactly where it is, but it's got to be something less than a half. Okay, and then they were happy with that answer. Well, as time goes on, they became less and less satisfied with that answer, and they said, well, we need to come up with a little better way to do this. Okay, and here's the approach or the process that they came up with. Okay, they decided, let's go ahead and let's split this region up, this region down below here. Let's split it up into rectangles, because rectangles are really, really easy to work with. Just base times height is our formula. Okay, and so they decided, well, let's just for right now, let's pick 4 rectangles. And let's split this region up into 4 rectangles that will really closely approximate this area. And what they decided to do was this. Well, if we're going to do 4 rectangles, and we're going from 0 to 1, my first question for you is, how wide is each of those rectangles? How wide should they be? I need to cover a total distance of 1, and I need to split it up into 4 equal rectangles, so we want a width of about a quarter, right? Just each one will be a 0.25. So the first rectangle will go from 0 to 1/4. The next rectangle will go from 1/4 to 2/4, and the next one will go from 2/4 to 3/4, and then the last one will go from 3/4 to 1. Okay? And so that's the first thing they did, was they kind of split this problem up, and instead of looking at it just as one big shape, we're going to split it up into 4 smaller shapes. Okay? Then from there, they had to decide, well, where am I going to draw the height of this rectangle? Okay? And on this first example, we're going to draw the situation which is usually described as like R4. We're going to draw the rectangles so that their heights are on the right side of each rectangle. So here's what I mean. Okay? I'm going to come over here to 1/4, and that's going to be the height of my first rectangle. And then if I finish drawing it off, here's what the first rectangle looks like. Okay? I'm going over to 1/4, and my height gets drawn from the right side of this rectangle. Then I come onto the second rectangle, and I'm going to draw the height on the right side, so I'm going to draw it at 2/4. So I draw the height at 2/4, and then I just end up finishing off the rectangle. I draw back to 1/4, and then just finish off drawing the rectangle. And then I go over to 3/4 for my next height. Okay, and so I get a picture like this, and then I come over here to 1, which would be my last height. Okay? Now, will it be very difficult for us to find the area of each of those 4 rectangles? And the answer is no. It's going to be very simple. And then if I go through and add those 4 areas together, is that going to give me a decent approximation for the area underneath this curve? Well, decent is probably the appropriate word here. Our answer will definitely be related to this actual area, though. It's going to be definitely way too big. Just like the triangle that I drew the first time had some extra section in it that we really didn't want. We definitely have extra sections here. We really don't want this, we really don't want this, or this, or this, but it gets us close to the right answer. Okay? So let's go ahead and calculate this, because we're going to change something up here in a little bit and calculate it a different way here. All right, so R4, the base of this rectangle is 1/4, and what would be the height of this rectangle? How would I get the height of this curve at 1/4? Yeah, it'll be 1/16. It'll come from 1/4 squared. So I'm at 1/4 for my base, and then the height of the function is 1/4 squared. I'm just going to write it that way for right now. Okay? All right, what about the second rectangle? The base is what? just this rectangle here, it is 1/4 again, and the height of the rectangle could be found how? 2/4 squared, right, or 1/2 squared, right. Okay, so I would add on another base of 1/4 and then a 2/4 squared. And we could simplify it to 1/2, but we don't really need to. Okay, what about for the third rectangle? What's its base? 1/4, and its height is 3/4 squared. Sure. And hopefully you're starting to see a pattern here, because here in a little bit we're going to be able to use some technology here, whether it's calculator or spreadsheet or something, to be able to speed up this process here. Okay? And then what about the last rectangle? 1/4 times 1 squared, or 4/4 squared. Right. Yeah. 1/4 times 4/4 squared. So we can definitely see a nice little pattern develop here. And if we were to go through and add up all these together, we would get an approximation for the area underneath this curve, and then we just realize our answer is going to be too big. Okay? Now, the other thing that I want to point out about this is that when we start to get ready to calculate this, to speed up the process, what can be factored out of all of these terms? We can factor out the 1/4 from each one. In other words, we can factor out the width. That's why we purposely let that width be the same on all of them. So we can go ahead and factor out that 1/4, and then our problem just becomes 1/4 squared plus 2/4 squared, 3/4 squared, and then 4/4 squared. Okay? And this will be something that's very easy to type into a spreadsheet or into a program on a graphic calculator, that we'll be able to get this answer coming out real quickly for us. Okay? All right, so that's the first one. That's how we calculate something called R4. Okay? Now I'm going to go ahead and erase this. You may want to just draw another example, okay, of the same picture. Because now we're going to calculate something called L4. Okay? And you can probably guess L4 stands for, well, instead of drawing the rectangle heights on the right side, what if we draw them on the left side? How will that affect our answer? Okay? All right, I'm going to start on over here for the first example. Okay? The first rectangle goes from 3/4 to 1. If I draw the rectangle on the left side, okay, the height of the rectangle is on the left side, there's my height. And then I'm going to come straight across this time, because I'm only going from 3/4 to 1. Okay? So here's the first rectangle that we get if we draw the left side. The next rectangle over, if I draw the height to 2/4, and then I come over, that'll be my second rectangle. Then I draw the height at 1/4. That'll be my third rectangle. And the reason I started on the right side is because the fourth rectangle has a height of what? It just has a height of 0, right? So the fourth rectangle is just basically this line right here. Okay? That's why I didn't want to start over here, because I thought that'd be confusing. Okay? All right. So on L4, if I was going to make this calculation, I would be finding the area of this rectangle plus this rectangle plus this rectangle, and then this one, just this rectangle, it's kind of there, but it has a height of 0, so it has an area of 0. So I'm finding the area of these 4 rectangles, or these 3 rectangles, and this nothing right here. Okay? So let's go ahead and see what that looks like. Okay? What's the area of this first one over here? Well, it's got a width of 1/4, and it's got a height of what? It's got a height of 0. So 1/4 times 0 squared. Okay? What about the next one? The width is 1/4 times the height is, here's my x-coordinate, so 1/4 squared, right? If I'm trying to find this height, that means I need to plug this x-coordinate in. Okay? So I'm at 1/4 for my width, and then 1/4 squared for my height. Okay, what about this third rectangle? 1/4 times 2/4 squared. Okay, and then the last one is what? 1/4 times 3/4 squared. Okay, and again, the nice thing is a 1/4 can be factored out. It's still that same base element that can be factored out here. And this time it's just 0 squared plus 1/4 squared plus 2/4 squared plus 3/4 squared. Okay? And I could go through and make this calculation and come up with a result. Now, what do we know about this answer compared to the actual area underneath this curve? Definitely less, okay? Because we can see we did not capture 4 of the regions here, okay? Now, what do you think the ultimate goal is here, though? Well, the ultimate goal is to find this area underneath the curve, okay? We did R4, and the answer was what? Too big. We did L4, and the answer was too small. So what do you think we're going to do next? We're going to average the two, exactly. One of them's too big, one of them's too small. So the next best thing is let's come in and let's just average those two. And I think the language that this book uses, or at least what I'll use, I'll just call it A4 for average. Okay? So if we were to go through and find this number, and I don't know what it is, but we can calculate it. We go through and find this number. And then if we average those two numbers, so L4 plus R4 divided by 2, that should give us a pretty good estimate of what this area is underneath the curve. And that's the process that was used a lot back, again, before calculators and before we could find these really efficiently here. This was the process used to estimate the area under a curve, and we still need to use it in some situations here today that I'll show you here in a little bit. Okay? If we don't have the function x squared, there's not going to be any way we can do an antiderivative. So we will have to fall back on methods like this when we have tables or graphs that don't have functions attached to them. Okay? All right. Now, there's one more method that is used besides R4 and L4. And some of you might have been asking this in your head already a little bit ago. Instead of drawing the rectangles on the left side or on the right side, where else might I draw the heights to get a pretty good estimate here? Because one of them was always too big and one of them was always too small. So where should we draw the heights? Instead of drawing it at 0 or drawing it at 1/4, what if I draw the heights right in the middle of the rectangle? And what we're going to call that is we're going to call that M4 for midpoint. So instead of drawing it on either side, what if we draw this right in the middle? Okay, and again, I'm going to erase just to start over here. Okay, so my first example, if I look at the first rectangle, I'm going from 0 to 1/4. How about if I draw the height right in the middle at 1/8? So I come in here at 1/8 and I draw this height up. This marker's drying out here. Okay? And my first rectangle would be right here. A little bit hard to see for some of you in the back probably. Okay, let's get to the next one here. The next rectangle, if I draw my height to 3/8 right here in the middle, okay, then I'm going to draw another line parallel to the one on the bottom and then just connect them together here. There's my second rectangle. Okay, the third rectangle has a height about right here. And then the fourth rectangle would be a height that's 7/8, so about right here. Okay? Now, just geometrically, just looking at this, we can see that this is a better estimate than either one of L4 or R4 at this stage. Okay? And the reason that we can see it's better, just if I look at this last rectangle, because it's the easiest one to see this on, okay, how close do you think, if I was just to draw, just to cut it off and just look at 3/4 to 1, if we looked at the area underneath of this curve and we found that area, and then I found the area of the rectangle, how close would those answers be? And it looks like they'd be really close. And the reason that I say that they're really close is this. Okay? If we just look at the area underneath the curve, okay, we're talking about this region right here. So all of this down here plus this little shape up in here. Okay? If I look at the rectangle, if I hide this region up here, that's all this area plus this piece over here, right? Okay? So both of them have this little section, and then the curve has this section and the rectangle has this section. But what does it look like how those two are related? Don't they look fairly close in area? Okay? And I know this is a really rough sketch, but that's actually what's happening here. This area is really close to this area, so the rectangle's area is really close to the area underneath the curve. And so midpoint formulas are also very good in an approximation. This average is good, but this midpoint is also a really good approximator. Now, what would it look like if we were going to write this out? What would midpoint look like? And then we're going to go to the calculator here and show how to get these answers typed in real quickly here. Okay, well, what's the area, or what's the base of the first rectangle? It's still 1/4. What's the height of my first rectangle? Well, we decided that's at 1/8. So I'm going to take 1/4 times 1/8 squared. Okay, and then the second rectangle also has a base of 1/4. The height is over at 3/8. So 3/8 squared. And then the third one would be 1/4 times 5/8 squared. And the last one is 1/4 times 7/8 squared. Okay, so all I did was, instead of picking the left or the right side, we just picked the value right in the middle of the rectangle. Okay, again, the nice thing is the 1/4, the base, can be factored out, and we just end up with a long addition problem here. Squared at the end there. Okay. All right, is there questions with how these are set up? Now, if you have your graphing calculators, go ahead and take them out. Because we're going to talk about, there's a nice little built-in feature here that helps calculate these sequences of values. Okay? And as soon as that projector comes back on, we'll be good to go here. Okay, and it's just about warmed up here. All right, the place that I am at in the graphing calculator, there's a list function right here above stat. And if you go to second list, okay, this is the place where we need to be for right now. Now, if you go over to the math column, the thing that we want here is choice number 5. We want to do a summation, which is number 5. We want to sum up all of these values together here real quickly. Okay, we'll do the R4 first, as that'll be an easy one to start with here. Okay, so if we wanted to do R4, we would go ahead and choose option number 5, which is sum. Okay, the next thing we're going to do is go back into second list again, and this time under operations, there is a sequence at the bottom there, number 5. Okay. So we're going to have the sum of the sequence. We're going to tell the calculator a sequence of numbers to add up. Okay, so sum sequence. Okay. Now, the first thing that we need to type into sum sequence is we always need to type in the area function. Okay. Now, how am I getting these areas, the areas of all these rectangles? Well, I'm taking the width of the rectangle times the height. Okay. Now, the width of the rectangle we know is always 1/4 in this problem, right? Because we specifically made it be 1/4. So I can go ahead and type in either a 1/4 or a 0.25. It doesn't matter. Okay. The next thing that I need to type in then is I need to tell it what these numbers will be over here. How are we getting all these numbers? Where was this 1/4 squared and 2/4 squared coming from? Well, weren't those coming from the original function? That's why the squareds are all on all those, because that's what the initial equation was. Okay, so I'm going to type in 0.25 times x squared. I'm going to type in the width times my function. Okay, and then we'll tell it here in a little bit what numbers to sub in. All right, so that's step 1, is type in your area equation, and for our case, it's going to be the width times the function. Okay, then hit a comma. The next thing you need to do is put in just another x and then a comma. All this is telling it is, now I'm going to start telling you what numbers to sub in for x. So you're telling the calculator, here's your x, here's the values to go in for x. All right, the third thing is, you're going to tell it the lowest number to type in for x. And if we're doing R4, the first number we want in for x is 1/4. So I'm going to put in another 1/4. And you can put it in as a fraction or a decimal, it doesn't matter. Okay? So the second argument is x. The third argument is the lowest x. The fourth argument is the upper x, or the last x you want it to type in. Well, the last x I want it to put in is 4 over 4, or 1. So I'm just going to put in a 1 here. And then there's one more argument at the end. The fifth argument is, how much of a step value do we want? How much is there of an increase between this x and this x? Between this x and this x, and so forth. Okay, and how much of a difference do we have? We have a difference of 1/4, right? From 1/4 to 2/4 is 1/4. From 2 to 3/4 is another 1/4. So we'll type in this step value of 0.25. So we're telling the calculator by typing this in, I want you to plug in some values for x, multiply them by 0.25. I want you to plug in 1/4 first, plug in 1 as that's where you stop, is at 1, and then keep going up by 1/4. So plug in 1/4, then 2/4, then 3/4, and then finally 1. Okay, we hit equals, and if any of you calculated this one out by hand, this is what you should have come up with, 0.47, really close. Okay, so that R4 value that we did at the very beginning has an area of 0.47. Okay, and we said that answer was too big. Okay, now let's do L4 here. The nice thing is, if you push second enter, it'll retype the whole thing because we just have to make a few small changes for L4. So what if we want to redo this so that we calculate L4 this time? Okay. As we look at the calculations up here for L4, do I still have a width of 1/4? And is my function still x squared? Yes, so I don't change anything in the first argument. Okay, I leave the x in the second argument. Okay, what about over here? Am I starting at 1/4 this time? No, where am I starting at this time? Starting at 0, right. So I need to change that 1/4 to 0. Okay. And if I push delete, I can delete off that fraction there. Okay, so I'm starting at 0. What's the last number I want to plug in for x? 3/4, right. I'm going from 0 all the way up to 3/4. So I can type in 3/4 or 0.75. And then what's my step value here at the end? Well, my step value is still 0.25 because the difference between each successive x, that difference is still 1/4. Okay, and then I punch this in, and I see this answer is really close to, and again I'm rounding here, 0.22. Okay, so the first result was too big at 0.46. The last result was too small. We decided that we could average the two if we want, and then come up with the A4, which will be a pretty good estimator. So if I take this answer plus 0.46875, and then divide it by 2, I think a pretty good estimator for the area underneath that curve is about 0.34. If we were to actually find this area, it'd be really close to 0.34. Okay? All right, so that's one way that this can be done. Now, what if we were typing in the midpoint formula? What would this look like? Okay? Well, I'm going to push second enter about 3 or 4 times here until I get back to the sum sequence. There we go. Again, I just don't want to have to retype it in, so I'm just going to let that built-in feature work for me here. Okay, if we're doing midpoint, okay, does the first thing change, or is it still 0.25x squared? Still 0.25x squared, right? There's no change because I still have a width of 1/4 and I'm still using x squared. Okay, x stays the same. All right, the 0 needs to change to a what? 1/8, yep. So I'm just going to retype over this. 1/8. What's the last x to go in? 7/8. 7 over 8. And then what's my step value? How much is it between each of those x's? How far is it from 1/8 to 3/8? 3/8 to 5/8 and so forth. It's 1/4 again, right? Okay, or 2/8, yeah, however you want to type it in. Okay. You may have noticed this already. Okay, some of you may not have, but this value down here for the step, how far between x's, that's always the same number as the width of your rectangle. Because the width of the rectangle, even if I'm at the midpoint of the first one, if I want to get to the midpoint of the next one, that's the equivalent in length to the base of the rectangle. Okay? And so if I type this one in and hit enter, this answer is really close, 0.32, 0.33. So the midpoint gave me a 0.33 estimate. The average gave me a 0.34 estimate. So I can guess with pretty good confidence that if we were actually able to calculate this area underneath here, that answer would be really close to 0.33 or 0.34, somewhere in that range. Okay? All right, now, here's the big jump in concept, though. And that's why I wanted to show you this first. What might we be able to do to get better estimates for R's or L's or M's or any of those? What thing that do I have control over in this situation where I could get an even better estimate? More rectangles, exactly. So instead of just doing 4 rectangles, how about if we did 10 rectangles or 100 rectangles or as many as we want? And that's where the technology is really nice, because it can do calculations very quickly for us, even if we want to do 100 rectangles or 1,000 rectangles. Okay? So let's just go back and let's rework this problem. Let's just start with R, but let's do R100 this time. Now, we would never want to do this by hand because we don't want to calculate 100 sums together by hand. So we let the calculator do this for us. Okay? Second enter. And I can actually go back and I can start clearing out most of this stuff. Whoops. Well, I'll just start over. Second list sum, second list sequence. Okay, I'll just start over because we're going to have a lot of changes on this one. Okay. Now, this time we're still trying to go from 0 to 1. But now we're doing 100 rectangles. Okay? Now, the rectangles are being drawn on the right side of the figure. Okay? So the first rectangle will be from where to where? Can you just tell me what the width will be on each of those rectangles? How much? 0.01 or 1 out of 100, right? Because I'm traveling a total distance of 1, and I need to split it up into 100 equal parts. So this is located at 1 out of 100. The next rectangle will be over at 2 out of 100, and so forth. Right, okay? So the width of each of my rectangles, 0.01. And then times x squared, just like before. Okay, so I just had to make a change. I don't have a width of 0.25 anymore, it's only 0.01. Okay, second argument is just x. That doesn't change. Okay, the third argument. Now, what's the first number that I want for a height? My first rectangle goes from 0 to 1 over 100, but where am I drawing the heights at? I'm drawing the heights on the right side. So where's the right side of this rectangle? The right side would be at 1 over 100, right? Okay, because I'm going to do the right side of the rectangle. So the first height occurs at 1 over 100, or 0.01. Okay, if I keep doing this and keep drawing them all on the right side, just tell me, where's the last rectangle going to be between? What are the two numbers for the last rectangle? 99 over 100 up to 1. What's the right side of that rectangle? The right side of that rectangle is at 1, isn't it? Okay, so the last rectangle, the last height will be drawn at the x-coordinate of 1. Okay, and then my step value is still 0.01, just like my width in the very first part. Okay, so what this is telling the calculator, it's telling you, the first number I want you to sub in for x is 0.01. And then go by 0.01. So the next number is 0.02, then 0.03, 0.04. And keep subbing those in until you get to 1, and then you stop. Okay? And it's going to add up all this for us. If we just push equals, this should be an even better estimate. Notice it didn't take very long, 0.338. And that's consistent with what we said before. We thought it would be somewhere between 0.33 and 0.34. And we are definitely between there. Okay? So this is good. Now, we can keep going with this. We can go up to 1,000 rectangles if we want. And if we just continue this process, more and more rectangles, we just get better and better answers as we make an approximation here. Okay? I'll tell you this, the graphing calculators, I don't know if I'd go any more than 500 rectangles. If you get up to 1,000, I mean, there'll be some lag time. It'll take it a little while to number crunch 1,000 rectangles, but it can be done. Okay? So you can do those calculations. All right, we'll see you next time. Bye.